Hey everyone, I am a first year of a PhD in Bordeaux, and I work with affine group schemes, in general with group schemes, but in this talk I would like to introduce you to affine group schemes and their action. So in the main part of the talk, I would like to tell you how the concept of group can be generalized to more wide situations. So, sorry. We will generalize the concept of group and of their actions, while towards the end, I will try to tell you how this is linked to what I study. Okay, so to begin, why is it interesting to talk about groups in general and of their action? Well, in different fields of mathematics, we find these objects. So in particular, we are used to, in topology, to talk about topological groups. And their actions are functions on topological spaces which are continuous. So we talk about continuous actions. Another example is seen in differential geometry, where people work with Lie groups and their actions, which are called the Lie group actions on differential manifolds. But this is something that is used also like in physics, where physical systems have some sort of symmetries. So it is interesting to make a group acts on systems, but also in probability, where we find a action of groups on measure spaces or probability spaces. So to see how the concept of group can be generalized, I will give you the definition of group in a way that may be a bit different from what you're used to, but it's the right way to define it in order to generalize this concept. So I recall that a group is nothing else than a set along with some maps, which are set maps. So a multiplication from G times G to G itself, an identity element. So we have a map from a single element to G, and an inverse map, which is a map from G to itself. And we want these maps to have some properties. So we want the multiplication of the group to be associative. And this traduces to ask the commutativity of the following diagram. So we want that if we multiply an element with the other two elements that have been multiplied in a way or in the other, we obtain the same result. Moreover, we want the identity element to be such with respect to the multiplication. And this is equivalent to asking that this diagram commutes. So we want that if we multiply each element of our group with the identity element, we obtain the identity. And finally, we also want that if we multiply, like for the definition of an inverse element, we want that if we multiply an element by its inverse, we obtain the identity element. Okay. So why is this useful to generalize the concept? The concept of group may be generalized to any family of objects with some particularity in which we can also add the structure of group. So in general, to give such a generalization, what we use is the language of categories. For people that are not keen with categories, just think a category as a family of objects. And when we talk about group objects in this category, we are also adding the structure of group to such an object. So in in particular, we need our category to have finite products. So let's see be a category with finite products. By definition, an object G in our category C, along with some maps which now are maps in the category C, as above, is said to be a group object in the category C. So a group object in a category C is an object along with some morphisms, which are now morphisms in the category we chose, that make the above diagrams commutes. So now the diagram are commutative diagrams where the arrows are in the category C. And this is called a group object. So for example, as we said, saw in the beginning, we have that if we choose C to be the category of topological spaces, then group objects in this category are topological groups. While you see that by definition, because of the definition I gave in the beginning, if we go back to the category of sets, then we recover the usual concept of groups. In fact, the maps that give the structure of group on a set are really set maps, so are maps in the category of sets. So now, this definition is also equivalent to asking that for each object X in the category C, we have that the set of morphisms from the object X to the group object G is a group. And actually, we have also some sort of compatibility of which you don't have to worry about. Okay, are there any questions so far? Is it clear? Okay, I think that my camera disconnected, but hopefully I'll be back. So what I would like is to specialize to the category of affine schemes. So let me recall briefly the setting. I recall that if A is any ring, then we may consider the set, which is called the spectrum of the ring A, of the prime ideals of the ring A. Okay, now this set actually is a topological space with respect to the Zariski topology. So what is the Zariski topology? We have that closed subsets for the Zariski topologies are those of the sort Vi, where I is an ideal in A. So Vi is the subset of the primes P which contain the ideal I. Okay. Now, by definition, an affine K scheme where K will be a fixed field for us is the spectrum of a K algebra. So is an object X, which is the spectrum of A, where A is a K algebra. Plus also another structure of which you don't have to worry about for this talk. So we will consider from now on the category C of affine schemes over a field K. So you can actually think of them just as K algebras. By definition, we have that an affine K-group scheme is a group object in the category of affine K schemes. So what is an affine K group scheme is an object G, which is the spectrum of a K algebra with the structure of a group. So in this case, if the spectrum of A is a group scheme, A is said to be an Hopf algebra. And 2 weeks ago, Jacopo talked a bit about group Hopf algebras, if you recall. So for what we saw before in a general category C, we have that in this case, if we take an object X in the category of affine schemes, so X is the spectrum of some K algebra B, we have that the set of points that I denote by G of X, so these are the morphisms in the category of affine schemes from X to G, is a group. And this is also equal to the homomorphisms, to the group of homomorphisms of K algebras from A to V. This is because of an equivalence of categories between the category of affine K group schemes and the category of K algebras. So this is why, this is because of what I told you, that you can think about affine K group schemes as K algebras. So I recall that here A is the Hopf algebra associated to G, while this B is describing our object X. So let's see some examples of group schemes. We can consider, for example, G of A, which is the spectrum of the polynomial algebra in one variable K of T. Now we have that for each K algebra R, GA of R, so here there is a bit of abuse of notation. With the notation above, it should be GA of spec of R, but since we are confusing K algebras with affine K schemes, we allow this notation. So these are the morphisms of K algebras from K of T to R. So an element here is a morphism phi, and each morphism is completely determined by the image of T. So T may be sent to any element R in big R. So we obtain that GA of R is equal to R. And we can see R as the additive group underline the K algebra R. So R is a K algebra. So in particular, we can forget about the structure of K algebra and the ring structure and just see it as an additive group. So in this case, this group functor, this group scheme GA is said to be the additive group over our field K. In a similar fashion, we can consider GM, which is the spectrum of K of T 1 over T. Now we have that similarly as above, we can see that for every K algebra R, GM of R are the morphisms of K algebras from KT 1 over T to R. And now, again, phi is completely determined by the image of T. But since T is invertible, the image of T must be an element R which is invertible in R. So we obtain that GM of R is the set of invertibles, and this is a group if we see it with multiplication. So this is can be seen as the multiplicative group underline R. And so the affine group scheme GM is called the multiplicative group scheme over K. Okay, I'll give 2 more quick examples. So we can also consider mu n, which is the spectrum of K of t over t to the n minus 1. So reasoning as above, we have that for each K algebra R, mu n of R is the set of elements small r in R, such that R to the n is equal to 1. And this is indeed a group with respect to multiplication. These are the n-thirds of unity belonging to the K algebra R. So mu n is said to be the n-thirds of unity group. Finally, if we consider a field K of characteristic P, we can consider alpha P to the n, which is the spectrum of K of t over t to the P to the n. So now you see that alpha P to the n of any K algebra R are the elements R in R, such that R to the P to the n is equal to 0. And now, since we are in characteristic P, this is a group with respect to addition. Okay. If there are any questions, don't hesitate to ask them. I don't know if I went too fast, if everything is clear so far. Okay. So I would like now to move to...
Is alpha a name?
Yeah, they are the elements that are that have index of nilpotence P to the n in R, but this actually is a subgroup of GA.
Yes.
And we see line it there.
Okay, just a curiosity. Thank you.
No worries. Okay, so I recall now the definition of an action of a group on a set, again in a way, in the right way, in order to generalize it to any category, as I did with the concept of group. So I recall that an action of a group G on a set X is once more a set map. So it's a map of sets that we denote rho from G times X to X. So we want this map to be compatible with respect to the multiplication on G. So we want the following diagram to commute. We want that if we multiply 2 elements and then we make the result act on elements on X, this is the same as if we first make an element act and then we make another element act. So this diagram commutes. Moreover, we want that the identity acts trivially on any element. And this traduces in the following diagram commuting. Okay, so with this definition, it is easy to see that we can extend this concept also to any category which has finite products. And in particular, we can see this concept in the category of affine schemes over field K. So let's see our fixed category. The action of an affine K-group scheme G on a K scheme, on an affine K scheme X is a morphism as above, which now must be a morphism in the category of affine K schemes, and the product in the category of affine K schemes is the fiber product. But so this translates on points. So if we fix any y in the affine schemes, we have that we obtain exactly an action of a group on a set. So I went a bit faster. If we have a K group scheme G and a scheme, an affine K scheme X on which this acts, this is a morphism rho from G times K times X to X, which makes the above diagrams commute. And on points, we recover actions of groups on sets. So I recall that G of Y is the group of morphisms from Y to G, while X of Y is the set of morphisms from Y to X. Okay. So how is this linked to what I'm studying? What I'm studying are the actions of infinitesimal group schemes. So what is an infinitesimal group scheme? An infinitesimal group scheme is a group scheme that topologically is just one point. So G is the spectrum of a K algebra A, and topologically, I will put bars to see that I'm thinking about the underlying topological space, is just one point. So we actually saw already two examples of infinitesimal group schemes. If we consider a field K of positive characteristic P, we have that alpha P to the N, which is the spectrum of K of T over T to the P to the N. Topologically, this is just one point. Indeed, the spectrum of such a ring is just the maximal ideal generated by T. I don't know if all of you are still familiar with these concepts. So I recall that this is a maximal ideal since if we take the quotient of K of T over T to the P to the N by the ideal T, we obtain the field K. Another example is given by, always in characteristic P, is given by mu P to the N, which is the spectrum of K of T over T to the P to the N minus 1. Now, since we are in characteristic P, this is actually topologically equal to spec of K of T over T minus 1 to the P to the N. And this is the only point T minus 1. Okay. So why is it interesting to study such actions? The aim is always to understand some properties of the acting group G, studying its actions on other schemes. In particular, the problem on which I'm working in general is related to the following problem, that is to understand what is the minimal number of parameters that are needed to define a general polynomial of degree n over a field K. So a general polynomial of degree n is of the form I wrote, where we consider the coefficients ai algebraically independent over a fixed field K. So I think all of us are familiar to the fact that if n is equal to 2, then a generic polynomial of degree 2, so of the form t squared plus a1t plus a0, may be reduced to depend by only one parameter. So can be reduced by a change of variable to be of the form t squared plus a, where, if I'm not wrong, a is equal to a0 minus a1 squared over 4. And it is not clear in general how to solve this problem in degree n. And what I study is at the origin closely related to this problem. So to conclude, I would like to give you an example of an action of a K-group scheme on a scheme. So we can consider this infinitesimal K-group scheme alpha p to the n. So I recall that this is the spectrum of K of t over t to the p to the n. And we can consider an action of it on the affine line. So A1, which is the spectrum of K of x. So I recall that an action of alpha p to the n on A1 is a map from alpha p to the n times A1 to A1. And on points, so what does it mean on points? That we are interested to define the action from the group alpha p to the n of R on the set A1 of R in itself. So what is the first object? The first object is the group of the morphisms from K of t over t to the p to the n in R, acting on the set of morphisms from K of x in R. And the easiest example of such an action is the one that associates at a couple of morphisms phi psi, the morphism gamma, which sends x to psi of x times phi of t. Okay, so this was just to give you an example. I will conclude, tell you briefly what tools I'm using, because maybe it's interesting for you to see, maybe some of you use the same tools in different fields, and it's interesting to see that they can be used also in such a setting. So I work with the ring of Ore polynomials, which are a particular non-commutative polynomial rings. And with Azumaya algebras, which are a generalization of simple central algebras. And actually, under some hypotheses, the ring of Ore polynomials are an example of Azumaya algebras. So why am I using these tools? This is because the problem I study reduces to studying some systems of equations whose solutions are elements in the K algebra of differential operators of the scheme X on which I'm acting, which satisfy the system of equations that I'm consider. And this system is defined by equations which are closely related to the group structure of the group G that it's acting on X. So, okay, this was just to tell you briefly what I'm doing. I don't pretend you to understand, but differential operators are non-commutative objects, and this is why I find myself trying to use the tools such as ring over polynomials, which are not non-commutative as well. So with this, I conclude my talk, and if you have any questions, I'll try to answer with pleasure. Maybe I put back on the camera here since my computer abandoned.